All right, EP, we got 17.4, the last K for a long time. It's called the solubility product, KSP, okay? We're talking about solids that do not dissociate completely, okay? So what we're going to be looking at is some salts that do not completely dissociate, okay? Calculate the solubility of a salt based on the KSP for that salt. So in a learning objective, we do have 3 that we have to do. So how do we calculate solubility, which is basically concentration? So solubility is concentration using KSP, okay? Man, I am just not working this highlighting stuff right. All right, the dissolution, okay, aka dissociation, okay? So the dissolution of a salt in a reversible reaction, equilibrium, whose extent can be described by KSP. And KSP, as we said, the solubility product. Now this is only, what you're going to see is a solid equilibrium, okay, which means did not dissociate completely. And this is kind of where students are like, but wait a minute, that's an ionic compound. And isn't every ionic compound a strong electrolyte? And those are called salts? Well, unfortunately, in this case, it did not. Yes, it's an ionic compound. Yes, it dissociated. But in this case, because of equilibrium, right here, we're going to change this. Get my little eraser on that S. We're going to call it a weak electrolyte. And because it partially dissociated, that's why we can call it weak. Okay, so this is when it gets a little tricky. If you would have saw just one arrow, like sodium, chloride, sodium, and chlorine, one arrow, 100% dissociates. Okay, and because it's 100% dissociate, you will not have a KSP because it completely dissociates. Remember, the whole point of K is that equilibrium. It did not completely dissociate. Okay, so that's the difference of it. The solubility, and solubility is concentration, okay, of the substance can be calculated from KSP from the dissolution of the process. Remember, dissolution, just a fancy way of saying dissociate, okay, or ionizes. Now, we have a chart right here. So under our course materials, under the KB, we have what's called KSP. So go get your chart, KSP. And what these are, okay, let's take this barium carbonate. So actually, let's look at the one that was in the notes. Barium sulfate, right there, okay. And that one was the one that was in the notes, okay. Barium sulfate will dissociate partially into barium and to sulfate, okay. Be very careful of those charges, okay. He has a KSP, according to that chart, 1.1 to the negative 10. Now, what do we know about this exponent? Okay, so the more negative that exponent is, that means it barely dissociated. Okay, it hit water, and basically what happens is you had barium sulfate in a solid form, okay, hit water, okay, and you pretty much still have the solid sitting on the bottom. However, you did produce some ion and you did produce some anion, but the solid remains undissolved. Okay, and you will see an AP question on this. I believe the one from the past they did was like potassium chloride. You'll see that one. Okay, so the majority of the solid just sitting at the bottom, and you can stir and stir and stir to the end of time, and it's still not going to dissolve. Well, look at these values. I mean, look at some of these. to the negative 28. This guy hit water, and it's mostly cadmium sulfide. I mean, he was not afraid of water. Negative 53. Oh my goodness. Okay, and notice we're talking about transition metals. Transition metals and water don't go really hand in hand. Okay, a lot of negative exponents. Okay, so these are solids that barely dissociated. Okay, you don't see too many like negative 2s, 3s, and 4s like you did for the acids and bases. I mean, these guys hit water, not even scared, not even scared. So a lot of these solids on here, you're noticing mercury, nickel, silver, cobalt, cadmium, lead. You're talking about mostly the transition metals. Okay, not too many group 1, because remember, this is the whole point of where a refresher of the topic from chapter 4, solubility rules. You're not going to see group 1 because group 1 always is aqueous. Okay, remember all those rules? You're not going to see too many halogens because most of the halogens, mostly, we're talking over 90%, most of the halogens, they do dissociate. Okay, so we're talking about mostly these transitions. The solubility rules, oh look, see, there you go, can be quantitatively, here comes math, related to KSP, in which the KSP values are greater than 1 corresponding to the soluble salts, because soluble salts are always greater than 1. So what they mean by this is that any of these guys, we wouldn't calculate KSP, but their values would be greater than 1 compared to the non-soluble ones. Okay, we wouldn't be calculating to begin with. That's why you're not going to see any sodiums, you're not going to see any potassiums, no lithiums, no. Okay, oops, going back, sorry. All right, so because barium sulfate is pure solid, the equilibrium expression depends on the ions of those, the concentration of those ions. Products of the reactants, ladies and gentlemen, we do not put solids in our KSP. Okay, the KSP is the equilibrium constant between the ionic solid solute in its saturated form. And what saturated means, very important chemistry word. Saturated means that no more solid could be dissolved. Okay, so you added solid and it dissolved. Well, that's not saturated. That means you got to keep adding. So you add some more solid until eventually you see no more solid dissolves. That's a saturated solution. Okay, very important term. KSP is called the solubility product constant because we're talking about how solids dissolve. So when we write KSP, and regardless, our KSP is always products over the reactants. You're not going to have in reactants because that guy was a solid, so nobody's going to be there. So your 2 ions right there. But the big beware, this is where it's going to get a little nasty. You're going to see coefficients. These are not like acids and bases. No acid and base ever had a coefficient. So if you have a coefficient, which I'll do one for you below, in general, the solubility product is equal to the product of the molar concentration of those ions, raised to the power of the coefficient. Okay, so let me show you what I mean by that. Okay, let's say we have this. I have calcium fluoride. Okay, and calcium fluoride, if I look on my chart, and I can find calcium fluoride right there. Okay, calcium fluoride has a KSP 3.9 to the negative 11. Okay, well, let's first write our balance equation. Calcium fluoride solid, and because it has a KSP, double arrow, I'm going to get my calcium plus 2. He's in group 2. Now I'm going to get fluorine ions, not diatomic ions, but I have 2 of them. So I'm going to move my coefficient in the front. Okay, now basic chemistry. Okay, right here I have a 1:1 2 ratio. I have twice the moles. So whatever his concentration will be, you will have not only twice the moles, but you will have twice the concentration. So when you write your KSP, It's your calcium and your fluorine to the second power, okay? But there's a but to this, okay? So what's going to happen is, let's say I don't even know these concentrations. I want to calculate. So I'm telling you, let's calculate the solubility, okay, of calcium fluoride. And all I know is that the KSP was 3.9 to the negative 11, okay? 3.9 to the negative 11, okay? I don't have anything here. So if I don't know these, okay, then this is where X comes in, okay? But here's the new thing, okay? And I'm going to do it right here above us, okay? So if you have like an ice chart, I'm going to show you eventually how to do this without the ice chart, okay? Well, solids, we can care less, okay? So initially, I don't have any of these. But what's going to happen is the change in equilibrium, okay? I need to gain some products, okay? So right here, I'm going to have my X, but this right here is going to be called 2X, okay? And then at equilibrium, I have X and still 2X. So I have my concentration X, and I have my 2X, and then squared. And that's going to give me my 3.9 to the negative 11. Okay? So 3.9 to the negative 11. And now here comes basic algebra. It's a little scary here. This square squares the 2 and the x. So right here I'm going to have x, and then I have 4x squared, okay, which equals that 3.9 times 10 to the negative 11. So now what happens when you take x times 4x squared? Well, this becomes 4x cubed. 3.9 times 10 to the negative 11. Okay, let's bust out those calculators. So how do you tackle this first? And sorry, I apologize, should have given you a little bit more room to do this. Okay, so first you need to do is divide by 4. Tackle that 4. So take that 3.9 E button, negative 3, divide by 4. And now I'm going to get x cubed, and it's going to be 9.75, and I don't care about sig figs till the end. Okay, 9.75. Now what you have to do is you have to take the cube root of each side. Okay, now usually, ladies and gentlemen, in your calculators you have, for those of you that have graphing calculators, you should have a button that says, I'm trying to remember how to get there. All right, so on your calculator, now this is for graphing calculator people, okay? Let me do this over here. You have a button called Math. So once you hit that button, and it should be over there on the left side, once you hit Math, because we're going to take the cube root, you should be hitting option number 4. And option number 4 looks like this, 3 cube, and then it has like this parentheses. Okay, once you hit option number 4, it'll automatically come up in the calculator, and then you plug in that 9.75 E button, negative 12. Okay, so then what happens is x is 2.1. Now we'll look at sig figs. 2.1 times 10 to the negative 4. Okay, now for those of you, if you don't have a graphing calculator in class, I will show you where your button is. Okay, so what did I just solve for? I'm trying to figure out their concentrations. And remember, at equilibrium, X is only calcium. But what's the concentration of fluorine? They won't be the same. I got twice as much fluorine, so I have to multiply by 2. So this would be 2x. So I'm going to take that 2 times 2.1 E button, negative 4, and I'll get 4.2 to the negative 4. And we got to put molarities on here, and this is what's called molar solubility. Okay, so if they ask you to calculate the solubility, they're looking for these two. Okay. All right. You guys are going to get some practice with this, okay, because you need to visualize what is happening here. In AP Video 7.11 to 13, around 10 minutes, okay, so this video right there, around 10 minutes, you guys are going to watch the video to it, and they're going to give you a ton of practice, okay, as you see, a ton. AP in yellow, they're shouting at you, okay, and tons of practice.